vector spaces. They're all called linear vector spaces because of the following. A set X is called a linear vector space over the field of real numbers R if the two operations, addition and multiplication by a scalar, are defined and satisfy the following axioms. So these are the axioms that I need so that all the above lie within this definition. For any three elements in that set, and for any three real numbers, so this is for every x and y and z in the linear vector space, for every three real numbers, the following are the axioms of a linear vector space. If I add x plus y, it's the same as adding y plus x. If I add x plus y plus z, if I add x plus y first and then add z to them, to the result, it's equivalent to adding x plus the result of adding y plus z first. If I multiply alpha, which is a real number, by two vectors, it's equivalent to multiplying alpha by the vector x plus alpha multiplying by the vector y. If I have alpha plus beta, two real numbers, multiplied by the vector x, this is equal to alpha x plus beta y. If I multiply alpha by the vector beta x, this is equal to multiplying alpha by beta, and then the result multiplying it by x. There exists a zero vector, and I put a hat over the zero vector just to differentiate the zero vector from the zero that belongs to the real numbers, the real number 0. So there exists a zero vector such that x plus 0, or such that for every a in x, a plus 0 is equal to a. For every x in the vector space, there exists x bar, or which we call negative x, such that x plus this negative x is equal to the zero vector. The last property, 1 multiplied by x. If I take x and multiply it by 1, I get x. Now, of course, for you, this, because we're so used to addition of real numbers, these seem to be very primitive or very trivial. But in a lot of the proofs, we're using all of these statements, which, yes, they do apply for linear vector spaces, but there are some things, there are some operations where these things do not apply, and that's why we need a rigorous definition of what we're actually doing. So, verify that the above sets satisfy the axioms definition of a linear vector space. If you look at all the sets that we defined above, here, you need to verify that all these sets actually satisfy these axioms for a linear vector space. And the other thing that we actually have not mentioned in the axioms is the zero element and the inverse element of additions. The zero element, number 6 and number 7. Are they unique? And for example, perhaps for R and R2 and R3 and Mn, it's very clear that the zero element is unique. It's just it's the vector or the matrix that has zero elements. But let's look at, for example, this space of functions defined on the interval 0, 1. Is there 2 or are there 3 zero elements in that space? Are there 2? For example, is this function 0 or not? A function that's defined 0 everywhere, but as another number but it has a certain value at 1, for example. Is this a 0 function or not? So the uniqueness of the 0 element and the uniqueness of the inverse element of addition can be proven using those axioms. So for example, and in your book, you have a few problems that you should look at. For example, the 0 is unique. To prove something is unique, you always start by saying, well, maybe there are 2 of them. Assume theta 1 and theta 2 are 0 elements. So this is the question. Is it unique? So we assume that theta 1 and theta 2 are 0 elements. Which means x plus x star is equal to theta 1. So the 0 element, so for every element in x, a plus 0 is equal to 0. So x plus theta 1 is equal to x. Now I'm going to apply this to theta 1 and theta 2. So instead of x, I'm going to use theta 1. Theta 2 plus theta 1 theta 2. I also have x plus theta 2 because I have 2 of them is equal to x. So I'm going to use this for theta 1. And if you look at the properties, x plus y is equal to y plus x, which means theta 2 plus theta 1 is equal to theta 1 plus theta 2, which means that theta 2 has to be equal to theta 1. Therefore, the 0 element has to be unique. And using the same arguments, we prove that the inverse element of addition is also unique. So far, we have defined what a linear vector space is. The next thing is we're going to define what a subspace is. So, for example, if you have R3, you can look at the plane is a subspace of R3. So it's a space within a space. So the subspace inherits the properties of the space. So the subspace A. So the definition. A is a subset of X. We have a vector space. A is a subset of X. A is a subspace if it is both if it's closed under addition and multiplication by scalar. Example. Consider R3. A is equal to 0, 0. X. X is a real number. A is a subspace of R3. This set A contains all the points along the z-axis. And so any two numbers, any 2 points along the z-axis, any two numbers that have coordinate 0, 0, and a real number, if you add them together, you're still on the same axis. So that's why this is a subspace of R3. So A is a subspace of R3. Consider R2. Again, B is a subspace of R2. What is B? Let's graphically look at it. This is R2, which is R and R. B is all the points along this line, or all the vectors along this line. Any vector here, and another vector here, if you add them together, you still lie on that same line. If you add 1, 1 plus 2, 2, you get 3, 3. 3, 3 is still on the same line, and so on. So this line forms a subspace of the bigger space. So, the dimensions of linear vector spaces. So R, we know, has one dimension. R2, 2 dimensions. R3 has 3 dimensions. Can those who are still awake, what do you think the dimensions of this linear vector space is that I just wrote on the board? Sorry?
Did you get the question?
Yes, what is the dimension of the vector space that I just wrote?
Two dimensions.
So 1, 2,
Two. This is subset of R2.
it's not a subset of R2. These are the functions that are defined on 0, 1 to R.
It's one dimension.
One dimension.
To R, yeah.
It's R. R is one dimension.
Yes, but this is not R.
It's two dimensions.
2. Did that? 2? So this is actually infinite dimensions. And that's perhaps why it's important to understand what the dimensions of a vector space is. So let's try to intuitively see why this is one dimension, 2, 3, and infinite dimension. So here, any vector is represented by one real number. Here, any vector is represented by 2 real numbers. Here, any vector is represented by 3 real numbers. Let's see what every vector here is represented by. A vector here is a function defined on 0, 1. So, what do I need to define this function? I need the value at 0. I need the value at 0.1. I need the value at 1. I need the value at every single point here. I have infinite dimensions. So, the more rigorous definition of what the dimensions is, we first need to understand or to define something called linear independence. And linear independence is defined as follows. A set of vectors v1, v2, vn in a linear vector space V is said to be linearly independent if none of the vectors can be written as a linear combination of the other vectors in V. Let's call this set A. Example, the vector x, which is equal to 0, 1, and vector y, which is equal to 1, 0, x can never be equal to alpha y. You can never find a real number that relates to x and y. So these two numbers, those two vectors, are linearly independent. X is equal to 0, 1, y is equal to 1, 0, z is equal to 1, 1, z is equal to x plus y, linearly dependent. So we've defined linear independence. So the second thing we have to define is a basis of a linear vector space. And please correct the typo in the new version. If you have the older version of the last year's version of the book, the definition is probably different. Slightly different. But here's the corrected definition. That's the final one. So a basis set of a linear vector space is a set of linearly independent non-zero vectors such that this set is in V, and any vector in that vector space can be represented as a linear combination of the elements of that set. Example, R2, if you consider the set x 1, 0 and y 0, 1, any vector in R2, there are two real numbers such that this V is equal to V1x plus V2. V can be written as a linear combination of those two elements x and y. Therefore, V, the set of vectors x and y, is a basis set for R2. And those two vectors are linearly independent. Now, x and y do not necessarily need to be 0, 1, 1, 0. Example, x is equal to 1, 0, y is equal to -1, -1. You will find for every element in R2, you will find two real numbers such that V is equal to a multiplier by x plus a multiplier by y. So we've defined linear independence, we've defined a basis set. The dimension is nothing but the number of elements in the basis set. The dimension of a vector space is the number of elements in its basis set. If you look at the ones that we define here, the basis set for R, you can choose one. Any number in R is a multiplier of 1. In R2, any number, any vector in R2 is a multiplier of 1, 0 and 0, 1. Its basis set has 2 elements. In R3, the basis set has 3 elements. In this set, any basis set will have infinite number of elements. Because you can define your basis set in different ways, but in any way, you can always, the basis set for V will have infinite number of elements. Maybe to make it, are you guys following? We'll give you 5 minutes just to.
Taping this year?
Yes. So that if you don't want to come,